Okay, welcome back. We're going to pick up here. Waves are classified by the way they move. So some waves move up and down, and we call those transverse waves, and some waves move back and forth, and we call those compression waves. So the way the wave moves is how they're classified. Well, the first one we're going to look at is called a transverse wave. And this is the one that most kids are familiar with. It's kind of like the way water moves, or if you shake a spring up and down. These are the waves that most kids learned about in elementary school. Okay? And in a transverse wave, the matter in the medium moves up and down compared to the direction of travel. And it's this up and down, it moves perpendicular to the direction that the wave moves. And an example is like this. Okay, so we have this wave, and this is the wave at one particular instant in time. Now, if we let the wave go, after a couple of seconds, it's going to look like this. Okay, this particle here is going to have gone up there, and this particle here is going to have gone down there. And then this one's going to go up here. So the wave's not just going to be standing still, because it is actually moving. And this is where we get the perpendicular motion of the wave. Okay, the particle that was up here is going to move down here, and the direction of the wave is straight. And you can see that this makes a perpendicular 90-degree angle. So the particle is going to be going up and down like this, and the wave direction is straight forward. Okay. And an example is like a guitar string going up and down, or people at a sporting event when they do the wave. Okay, the people stand straight up in their chair and sit back down, and the wave moves perpendicular through the stadium as the people go. And again, it's a good example of the people don't actually move along with the wave. They move up and down, but they don't actually change seats and go with the wave. Okay, the rest, or normal position, okay, is represented by this dotted line. And this is like a swimming pool when there's no waves. The water is just smooth. So it's this dotted line. If there were no waves, this would be like where the water would be on the tile before you jump in and make waves go up and down. So some of the water would be above that, and some of the water would be below that, because some of it's up here in this part of the wave, and the water that's up here in this part of the wave is not down here, and it's missing. Okay. There's different parts to the wave, and the crest is the highest point of the wave, so it would be here. And the lowest point of the wave is called the trough, and it would be down here. So as this particle moves up and down, it becomes, it's at the crest, and then it moves down and it's part of the trough. We're going to take a look at this little clip here. This is only a few seconds, and it shows the motion of transverse waves.
Waves carry energy, but not matter, from one place to another. For example, a rock thrown into a pond next to a bobber causes the bobber and the pond water to move up and down, while the energy waves generated by the rock move towards the shore.
Okay, so this is again an example of the wave is carrying energy, but the matter, like the bobber, stays in the same place. It just bobs up and down.
In other words, the bobber and pond water, which are matter, remain in the same position on the pond, while the energy carried in the wave travels across the pond to the shore. The action of the wave on the water is perpendicular to the direction of travel of the energy along the wave. If we fix a rope at one end and move the other end, we can also produce waves. The waves produced by throwing a rock in a pond or moving a rope up and down are called transverse waves. Transverse waves have a number of characteristics. A trough, which is the low point of the wave, and a crest, which is the high point. The difference in height between the crest and the trough of the wave is the wave's amplitude, and the distance between the crests is referred to as the wave's wavelength.
Okay, welcome back. This shows how a transverse wave moves. And I like this animation because we can see that this particle here, okay, is going up and down. And I added this line to the wave, okay, and the particle is going up and down. And it's the red particle doesn't travel with the wave. It's just going up and down, but it's staying in this particular place. And the wavelength is, any 2 points on the wave. And so it stays the same as the wave travels. And here's that whole perpendicular thing. The wave is moving this way. This is the direction of the wave. So I added this arrow here to show the direction of the wave. And then the particle is moving up and down. So it's moving up and down perpendicular to the direction of the wave. Now the other waves move is back and forth. And a lot of times we use springs to demonstrate this, like a slinky. These are called longitudinal or compressional waves. And in this case, the atoms move side to side or back and forth in the direction the wave travels. Because they're moving back and forth side to side, they're parallel to the direction of the wave travels. So in this case, we have this compressional wave here, and the direction of the wave is this way. Okay? And the particles in the spring are going to be moving back and forth the way I put here. And this is parallel. So the wave's going to travel this way, and then the parts of the spring are going to vibrate back and forth, but they're not actually, these coils aren't actually going to move along with the wave. An example would be spring, and sound also moves this way. The dense regions, the dense parts of the waves where it's compressed together, are called compressions. So where it's squeezed together and the particles are close, this is a compression. And then this less far apart of the wave, okay, is called the rarefaction. So that's a new word. It's probably going to be a little bit harder to remember than the other one. So we have compressions and rarefactions. I'm going to take a quick look at this little clip on the compressions and rarefactions.
A second type of wave is a longitudinal or compression wave. In a longitudinal wave, the particles of the medium.
Notice how the particles in the medium are moving back and forth. And as we said, they move back and forth parallel to the direction of the wave.
Carrying the wave also move.
You can see that these are supposed to represent the particles as they move through the compressions, and this is the rarefaction. The actual matter is not moving along.
Move back and forth. Unlike transverse waves, however, the particles of the medium move in the same direction the wave moves, not perpendicularly as in transverse waves. If a sharp force is applied to one end of a spring.
Now think about this. The actual spring itself, the coils of the spring, the metal doesn't move along with the wave. The energy of the wave goes through the spring.
A longitudinal wave travels along the spring. The wave moves the spring's coils closer together.
So you can see the compression and you can see the rarefaction.
As it passes along them. After it passes, the coils move apart again. The areas where the particles are closer together are called compressions, while the areas where they are farther apart are called rarefactions. The wavelength of a longitudinal wave is measured between the center of compressions or rarefactions.
Now, I like this animation, again, because it shows how, and we said sound waves move this way, and think of this like a speaker. When a speaker vibrates, it pushes in and out like this, or like a guitar string vibrating back and forth, or the head of a drum popping in and out, or even your vocal cords. Okay? As it pushes, it makes a compression. And then is like if the speaker was going back, the cone of the speaker, it would make the rarefaction. So you can see how it pushes the air molecules together and then pulls apart to make the rarefactions. So we see that the wave is traveling this direction, like this compression is traveling along and going this way. But the energy is going, like if this was air, the energy would be going through the air, but not taking the air with it. And the particles would be vibrating back and forth, but they would be staying, relatively in their same spot. So I added this line by this one red particle, and you can see it's moving back and forth here, but it doesn't actually travel with the wave. And then the direction of the wave is here. And this is the parallel part. It's moving back and forth parallel to the direction of the wave. And sometimes this is kind of hard for kids to imagine, but think about like when somebody talks or you're listening to music or something, okay, as the sound goes by you, which are like these compressions, it doesn't take the air with you. It's not like if you're listening to somebody, there's like a wind going by you with the sound. It's because the air is moving in these compressions, but it's not actually like moving and creating a breeze. Okay, so the red particle doesn't travel with the wave. It's vibrating back and forth parallel to the direction of the wave, but it stays basically in its original position. And this is the parallel part. And then the third type of wave motion is a combination. And a lot of times these are called surface waves, okay? And it's a combination of both transverse and longitudinal waves. So down here I put a longitudinal wave and a transverse wave. And remember the transverse wave, the matter is moving up and down, perpendicular to the direction of the wave. And then in the compressional wave, it's moving back and forth parallel. Well, if we combine these two motions, the up and down and the back and forth, we get the up and down and the back and forth. Well, if you're a particle and you have to get from here down to here, but also from here to here, you're going to end up going in a circle because you have to go over here to down over here and then back around. So these combination waves, the matter ends up moving in a circular motion as the wave goes through the thing. And here's a demonstration of how the particles move in these surface waves. Okay, so you look at the particles or the red dots, they're moving in a circular motion. Okay, a lot of times they'll use something like a duck on the water, and he goes in this circular motion. Okay, and there's, he's going up and down and up and down. He's also going back and forth. So he's going from here to here and from here to here. Okay, so when you combine the back and forth movement of one and the up and down movement of the other, you end up with this circular motion. We're going to take a look at this little video with Bill Nye, where he gives us a good example of how seismic waves carry energy. And seismic waves are what make up earthquakes. So his demonstration is going to be specific to how an earthquake can start in one place and knock a building down way over there. Okay, often combination waves or surface waves are called seismic waves. And Bill is going to give us a demonstration of how seismic waves or those combination waves can transfer energy. And a lot of times they're earthquakes. So he's going to give us an analogy of an earthquake here.
Earthquakes can travel in waves. Yeah, sometimes an earthquake over here in North America can be felt all the way over here in Africa. That's because they're waves, some of them going right through the earth and some of them going along the earth's surface that carry the energy of the earthquake from here all the way over to here. Take a look at this. It's our plastic Earth surface wave model of science. And this blue pad represents the Earth's surface. Now, the surface of the Earth is floating on molten liquid rock, but here it's floating on liquid water. So watch what happens when we make a wave over here.
Now remember, one of the key things about waves is that they transfer energy.
It can go from here all the way over there. Watch. And look, the wave in the pad, in the surface of the Earth, can make this building fall right over. Of course, it's not really a building, it's a model of wooden blocks.
Understood, yeah.
But anyway, earthquake waves are called seismic waves. Seismic waves. So they're waves that move through a whole planet.
Okay, we're going to stop here and pick up here next time. I want you guys to answer these questions on your own. I hope you're having a great day, and we'll see you soon.